Hi everyone, my name is Kartik and my channel is about mental models. In this video I will be talking about Bayes' theorem and or Bayesian thinking. Bayes' theorem is a mathematical formula which we can use to work out a conditional probability. A conditional probability is simply the probability of an event given that we assume, presume, or know another event has also already taken place. So, in essence, it's the probability of what we want to know given what we already know. And sort of this line here represents the word given. Now, looks a bit complicated, but let's work through a scenario. Let's say there is a class of 20 children. What is the probability that we pick a student that owns books and reads? So let's draw a Venn diagram. So this circle is that they read. And this circle is that they own books, the students own books. So there are 4 students that own books, there are 7 students that like to read, and different colour, let's say there are 3 students that own books and like to read. And there are also 6 students that don't own books and don't like to read. So this is my class of 20 students. Now, if I sort of put the probabilities, if I write the probabilities out, so in a table, let's say I've got sort of read here, not read here, and they own books here and do not own books here. So I've got this little table. So if the student owns a book and they like to read, it's 3 out of 20, which equals 0.15. If they own a book and don't like to read, then we're in this territory here. So that's 4 out of 20, which is 0.2. And the total is sort of adding these two up, which is, do they have a book? 7 out of 20, which is 0.35. Now in the no book section, if they do not own books but they like to read, that's this portion here. So again, 7 out of 20, which is 0.35. They have no books and they don't like to read is this number down here, which is 6 out of 20, which is 0.30. Now the fact that they just don't have any books, irrespective of if they like to read or not, just add the 2 up. That's also 13 out of 20, which is 0.65. And if we sort of add the probabilities going down vertically, then you've got the total here, which is 10 out of 20, which is a half, and again 10 out of 20, which is a half here. So these are the probabilities for this Venn diagram and our little class of 20. Now, going back to the question, what is the probability that we pick one student from our 20 that owns a book and likes to read? So the probability that they own a book and like to read. So own a book, like to read, it's this square here, it's 3 out of 20, which is 0.15. What about the probability that they own books and they don't read? So I'm going to call that an XR. So they own a book, but they don't like to read. Well, that's this square here, which is 4 out of 20, which is equal to 0.2. So this was simple probability. Now let's go further with the second example, which is this one here, using conditional probability. What about the probability that they own books but don't read, given that we know they own books? So it's the first part of it is books and don't read, but we have this given line now because it's a conditional probability, given that we know they own books. How do we work this out? So this can be worked out by essentially taking the probability of the fact that they own a book and don't like to read and divide it by the probability that they have a book. So it's this section of the conditional probability that goes on the top and this goes on the bottom. And so mathematically it is, what is this? It's 4/20th divided by the probability that they have a book, which is this one here, 7/20, which gives you 4/7, which gives you 0.57. So that's the probability of they have or they own a book, they don't like to read, given that we know they own a book. Now let's change this slightly and say, what about the probability that they own a book and they don't like to read, given that we know they don't like to read? So here we're changing something very slightly. So again, this is broken down and worked out by putting this portion at the top. So own a book, doesn't like to read or doesn't read, divided by this portion, which is the probability that we know they don't read. And so again, the top portion is 4/20, but here the bottom portion, which they do not like to read, is 10/20. We divide the two, we get 4/10, and so that is 0.4. So in both cases, in this case and in this case, in both cases, even though we want to know the probability of the same event, that they own books but they don't read, which is this portion here, the difference between the two, these two numbers here, 0.57 versus 0.4, is due to the different knowledge we have. In other words, going back to this generic statement here, what we want to know, this portion is the same, but what we already know is different, in that for one scenario, what we know is that the student owns a book, and in the other scenario, we know that the student doesn't read. So our evidence, or our prior knowledge of what we already know, is different, and that's what leads us to the different probabilities. Now, in both of these cases, let's say we don't know the probability that they own books but don't read. So we don't know this. Let's say we don't know this. Or in this table, we don't know this number, this box here. Can we still work out this, the probability that they own a book and don't like to read, given that we know they don't like to read? Yes, we can. And the way we do it is, if I put it here, if we say the probability of a book and doesn't like to read, given that they don't like to read. Now, previously I would have just put that portion on the top, but we don't know what that portion is. So the way we get around that is by saying it is the probability that they own a book and don't like to read, given we know they have a book, multiplied by the probability that they have a book, all divided by the probability that we know they don't read. And so this looks like a complicated formula, but this is the way around it because we don't know this absolute probability of them owning a book but not reading. And so this is the way around it. And if we plug in the numbers, what we have is, for this one, we have 4/7, which we've worked out here, multiplied by the books, which is 7/20, divided by probability that they can't read, which is, they don't read, sorry, which is down here, 10/20. So if we put that all in to our calculator, what we will get is, let's say 0.57 times 0.35 divided by a half, which gives us 0.4. And lo and behold, that's the same number. And so it works. We can calculate what we want to know, which is the same thing here, without knowing this absolute probability of how many students own a book but don't read. And this method works because this is actually Bayes' theorem. Now you might think, so what's the big deal here? In this case, because we know the simple probabilities, because we have this table or we have this Venn diagram, it isn't earth-shattering because we know all the probabilities. But where we have gaps, which is often the case in reality, this theorem, this method, gives us an ability to solve for what we're looking for by putting another probability in which we do know. So what about Bayesian thinking? Well, I said it's about Bayes' theorem. This video is about Bayes' theorem and Bayesian thinking. So what about Bayesian thinking? Well, we have been doing that through this example without even realizing. But before I define it, let's look at one more iteration. Let's say in this last example, the probability that we have a student that owns a book doesn't like to read or doesn't read, given that we know that they don't read, but we don't have the exact probability of this, that a student owns books. We don't know what that is. So let's say before we had the values here, which is a student owning a book is 0.35, but let's say we don't have that. Let's say we are estimating, we estimate the probability of a book to be 45%. Now what? So again, and we know the other probabilities, they're unchanged. So again, what we would do here is we would just plug that number in. So instead of 7/20ths, or let's say it's 45%, so let's just go up here. We'd plug this number in, so it's 0.57, that's the same probability, that's not changed, and we know that, times by 0.45, which is this here, the 45%, divided by a half, because we know that probability hasn't changed, and that gives us an answer of 0.51. And so here, the answer has risen. So this answer has risen compared to the original answer. And that's because we estimated the probability of students owning a book, irrespective of whether they read or do not read. Now, you may think that guessing is a bad thing, but if the population is really large, then this is the only method we have to help facilitate the calculation. So if we didn't know this, we would have to guess it. And to add on to that point, in reality, we encounter new information all the time. This information can be fuzzy and or limited, but still useful. And so when we learn something new, we should take as much as is possible of what we already know into account. So the new information essentially shouldn't push out the old information. And so a Bayesian thinking approach is to take into consideration and to use all relevant prior information when making decisions. So whether we know this, whether we know this, whether we estimate this, we're taking all of what we already know as best as possible when making decisions. And so Bayesian thinking is a form of reasoning which involves updating probabilities, like we've done here, as new information becomes available. And that is essentially what the Bayes theorem and Bayesian thinking is about. Now, I could talk more on this subject and go through more examples, but this is actually it. And by talking more, I will probably stray into the realms of probabilistic thinking, which is one of my future videos. So I'm going to stop here with Bayes theorem and Bayes thinking. Thank you for watching. If you haven't done already, please watch this video on distribution, as it will help in the understanding for the probabilistic thinking mental model video, which is coming soon. And I will see you all in the next video. Thank you for watching. Bye bye.